In this paper, we introduce a novel speech-based workflow for quick and dirty 3D shape exploration in early design. We are inspired by the importance of verbalization in facilitating design cognition, specifically in the context of form exploration. Through our workflow, we aim to study the fundamental principles that are necessary to operationalize speech as a viable means of describing and communicating 3D shapes. Our first step towards developing such a workflow is to introduce a convenient way to create semantic shape representations. We use LOFs as our 3D modeling technique as they allow us to explore a wide variety of 3D shapes by simply changing their 2D profiles and guide curves. In addition to the generalizability of LOFs in creating geometric shapes, they provide a convenient method to be utilized with verbal descriptions. As such, hierarchically segmenting LOFs into objects, parts, and regions can help us map verbal descriptions to these segments. In our workflow, we use guide curves to define the outline of the 3D objects present in our scene. The control points of the guide curves are used to segment the objects into parts, which are further divided into regions. The guide curves are represented as splines, or a combination of splines and straight lines. A change in the dimension of the object, part, or region is mapped to the change in the position of the respective control points. We use a superformula equation to generate the 2D profiles of the LOFs. The superformula is a parametric equation that can generate a wide variety of shapes when the values of its parameters are changed. We choose a superformula for two main reasons. First, it allows for an overview then detailed creation of shapes. For instance, in our work, we can create a 6-sided polygon and then a 6-sided star by simply reducing the value of parameter n1. We can further make a 4-cornered star by changing the value of m to 4. Second, the parameterization of the equation allows for a natural mapping between the verbal and mathematical description of the shapes. While we aren't able to create all kinds of shapes with the superformula, it gives us a constrained yet useful way to semantically represent shapes from verbal input and conduct systematic user evaluation. After defining a semantic shape representation method, we use 4 main aspects to guide us in the design of our system. The first aspect is that of the design in context, which we provide through the context of a scene that consists of 3 pots and a lamp on top of a table. Using this, we aim to study how designers create and explore shapes with respect to each other. Next, we focus on order independence by allowing users to explore objects in any order they want. This helps us observe if an underlying sequence exists in the way designers explore the scene using their speech. We then focus on the semantic regions of interest, which we highlight in our workflow anytime the user makes changes to them. This helps us understand the effectiveness of using speech to interact with the regions of 3D shapes. Now, we focus on multiscale exploration specifically for shape modifications. We provide the ability to create overview then detail as well as direct detailed changes to shapes. We will now show this interaction in our system. Can you please make the lampshade hexagonal? How about making the lampshade starry? Okay, now can you make the stem 3-pointed star? Finally, can you make the lampshade smooth, please? We now change focus to size modifications. Here, we provide the ability to make coarse as well as relative size changes to the objects. I'd like the pot to be 30% smaller, please. Can you also make the neck smaller? I want the mouth to be 50% bigger. Okay, can you now make the body 40% shorter? We evaluated our workflow by conducting 6 user trials. After practicing with our system, users were asked to create a wide variety of scenes in 30 minutes. Here we show the scenes created through 4 user trials. Users were able to utilize the context of the scene to their advantage while exploring the different objects. Some users preferred uniformity between objects, while others tried to make each object unique. Users also preferred making changes to the regions of specific parts such as the stem, instead of the entire part. We further evaluated our system through user feedback. Users found our system easy to use and felt confident in doing so. They also found the activity engaging and felt creative and artistic through the process. Our workflow allowed us to successfully show the ability to semantically represent shapes using speech with the combination of lofts and the superformula. In addition to this, we were able to gain further understanding of areas of focus for future speech-based interface. For more information, please refer to our complete paper. Thank you for watching our video.